Right, so hi everyone, thanks so much for joining me today. Can you see my screen?
Yep, it's looking good.
Oh, brilliant. Okay, so yeah, let me introduce myself. I'm Laksitha Ranasingha. I'm a lead engineer, and I've been mainly working on backend development, especially around microservices and mostly on JVM. And yeah, last couple of years, actually, I got a really good chance to work on Kotlin, and I really loved doing Kotlin. And also today, I'm gonna look at one of those really nice features called coroutines, which is a first-class feature in the language, and you can take that advantage of that without using the complicated library. And also for the backend development, Kotlin is getting more traction nowadays because, like Luca mentioned, and also Raul, you see that lots of Android world, it's not that new, but in backend, especially for microservices development type of projects, now people, developers try to adopt Kotlin. Right. So today's agenda is I'm gonna briefly talk about the concurrency versus parallelism, and also how usually a program, process, and threads work, and also coroutine as a kind of a general concept, and move into Kotlin coroutines. And I would show that how these Kotlin coroutines work internally and under the hood, and also one of my recent experience, and we hope that we get a few minutes for questions. All right. Okay, so quickly, I'm gonna lay the foundation about this concurrency versus parallelism, because why we need concurrency and why we need parallelism is mainly because we don't want to wait, do multiple things at the same time. But I'm sure this concurrency and parallelism come always together, and then sometimes people get confused. Why? What is the difference? So I quite liked what Rob Pike mentioned about concurrency and parallelism. So basically, concurrency is dealing with a lot of things, and parallelism is doing a lot of things at the same time. So that means for concurrency, we can do concurrent programming with single thread, but parallelism we can't do it in true parallelism. I mean, we have to have multiple threads and multiple processes, of course, running. So that means single thread concurrency you see in JavaScript world, Node.js, it is event loop based concurrency, and parallelism is one way of doing concurrency, and another way is doing via coroutines. So the coroutine is also known as interleaved processing. So let's now move into coroutines. Actually, before that, I would like to again, talk about quickly how, usual computer program nowadays is not a disk but SSD. So you can see that programs are a set of instruction and loaded into the RAM, and then you see the processors are here, and inside the processor you see weekly threads. And that's an important part I want to highlight is there is always scheduler, and also you have context switches and preemption. Those type of heavyweight operations happen when you have threads, and that's why threads are, people call, they are expensive. They need always intervention. But threads are not bad or anything. I mean, I don't see that some of the challenges we see in the threads are also present in coroutines and higher abstractions level as well. But if you have done multi-threaded programming, you know that all these dangerous things and all the riskier bits like starvation, rest condition, deadlocks, all these nasty things which you have to deal with if we are not really expert on what we're doing. For these, the abstractions like futures, promises, actors, and also coroutines, basically, they help developers with try to minimize this risk. So that's the benefit of all these abstractions. So So it becomes more productive, developers are more efficient and easy to work with. So now I'm going to talk about coroutines as a concept. Coroutines are mainly the lightweight cooperative construct that allow developers to be able to write concurrent code in sequential fashion. That's very important, the three words, lightweight, cooperative, and sequential, because they're not threads. So like I showed earlier, you don't have to have a OS schedule or something to schedule or handle coroutines. So because of that, you can create hundreds of thousands of coroutine in a single JVM thread process. So also they're cooperative because coroutines run in a special block called coroutine scope. And also because of that, they know there's a parent and child relationship, and also they have a special way of communicating via channels, and also they are cooperative because coroutines get suspended and they can get resumed, and they normally give a chance to another coroutine, so another processing task. Because of that, you call them cooperative. What's the sequential code? The sequential code is like, if you've done non-concurrent or multi-threaded program, you can reason the code very easily, because you write the code in instruction one by one, sequential fashion. But if you think about threaded threads, multiple threads, or if you want to use the callbacks or futures or promises, you become ugly. You have this callback here, or could become it up in like very complex, hard to read code. So that's why another benefit, for the readability and easy to debug, those type of things come with coroutines because of the way we sequentially organize the code. Like I mentioned, coroutine is not something new. It's very, it looks new feature and trendy feature, but it's been around for decades. And you see many languages nowadays, they have coroutines. Especially, I like the way Golang is doing coroutines, because you can see that it's a single, one keyword, and then you put the function in front of it, it becomes coroutine. Runtime handles most of the things. And the Kotlin, again, something close to some user-friendly constructs, like builders. So we can see that you can launch a coroutine here, and you can execute your business logic inside that coroutine scope. So that's just about coroutine as the concept. And now we are going to look at Kotlin coroutines. So taking what we just talk about, sequential and cooperative, and also lightweight attributes of coroutines. So they also, the key components of Kotlin coroutines. At the same time, it has clear exit and entry points. So the reason was, if you look at this code on the right-hand side, you see that usually in a coroutine code, you have this the blocking and non-blocking world. There's a bridge called run-blocking coroutine builder. When you have that kind of function inside this run-blocking builder, you see you can launch any number of coroutines, or you can do any other processing, but the thing is they are confined most, and also they are they have a special parent and children kind of relationship. So that's a benefit. So they're like thread-like, so you can easily see that you can run 100,000 coroutines without being running out of memory. So that's very special. And so this is something that's probably one of the major advantages again, usual vanilla threads. Okay, now we're going to talk about one of the most important points, which is how do Kotlin coroutines work under the hood? It is something I wasn't sure until recently, because normally we have this abstraction, nice API, and we can just keep coding. But if you look at how they work, it's basically they have three major points. One is called suspension points. The other one is called continuation, and we will have a state machine. So based on three concepts, this Kotlin coroutines achieve this cooperative multitasking. Just manage each other, and they don't get blocked, and they get suspended, but they get resumed later. This attribute, all these nice features come into life because of three main concepts. So on the right hand side, you see this simple coroutine code. So you have the main method, and you have one suspension points at multiplied by 100 method, and another one at divide by 10, I think. So I just made this simple code to showcase this concept. So you see that these two are suspension points, and everything else is usual, non-suspendable functions or code. If you look at the same code in a way, which I mentioned earlier, we have suspension points now, and then how compiler knows when to suspend and when to resume, and also how compiler or the runtime actually keeps track of the things like variables, a temporary state, or state management. Basically, how does it do? So the basic idea is like that. When you meet a suspension point, like line number 3, anything before that up to this line 3, label at, let's say, label 0, and then if goes on, and then there's another suspension point at number 5, you see another label called label 1, and also the last one is label 2, which is usual print line. So the compiler knows, okay, I have to break this code down to 3 blocks, and label them, and keep the labels. And how do we keep these labels? There's a special object called continuation injected into these methods. For example, if you see this multiplied by 100, it takes only one parameter. But once it compiled, if you look at the decompiled code, you see that there's another parameter called continuation, which is the state tracking object. You use this to keep the result or any other runtime construct we want to efficiently and also correctly execute these coroutines. So let me show you that actually let me show the code which I so this is example code, I showed on the slide, but at the same time I just decompiled this into a Java code. So you can see that it's very ugly and a long code, but this is a major thing I want to show is, if you look at one of these multiply by 100 code. So look what it did. It injected this continuation object. So the continuation object is, if you go on to the next slide, you can see it's an interface provided by a Kotlin standard library. And also we have this method called resume with, because it knows it can resume the execution or maybe handle the error depending on the outcome. So that's one of the key points. So you have this continuation object, and then you pass this into the suspendable function, and you see there are switch cases which actually maintain the label. Depending on the label, you switch back and forth. Or maybe if there are default case, which is no label set, you can probably say it's it invoked before resume. Likewise, you just nicely handle these states using these continuation objects and also other builder functions. Right, so then you just saw that the code it's not that readable. It's just decompiled code, but I wrote this pseudo code extracted from that actual Java code. So you see that the basic idea is like you have a label, and depending on the label, you just go to the right coroutine, and then you can come back to the another coroutine, or give the queue a chance to run execute while the other coroutine is doing its heavyweight or slow processing. It's just based on the label you switch between these coroutines and also other runtime tasks. So the state machine, like I said, it's just something simplified version. It looks like this. So you have a clear entry point, and also you have the exit point, and then you normally set the state at the beginning. And if this multiply by 100 function takes a lot of time, it will get suspended. And then after a while, once it's completed, it comes back and then goes to the next stage. Let's say it set the label as level 2, and it will give a chance to divide by 10 async function to run, and then moves on by exiting here. Maybe we can say we are setting the label to the -1. So this is a kind of a state transition in a coroutine world. So now I would like to talk about one of the recent projects I worked on. So let's say we are going to build a conversation platform for the users who can basically ask about their orders, train times, or anything which is basically for customer services. So the idea is like if you bought something from John Lewis's and if you want to see where your order is and whether you want to reschedule your delivery, those type of things nowadays you can talking to Alexa or maybe talking to Google Home. Those type of smart clients are capable of answering those type of queries if you integrate and if you provide right APIs and do the processing. So the system architecture is like this. This is like a very simplified version of it, and you see this NLP engine. It takes a text and then try to get the intent of the user. For example, if you say, "Where's my order?" So this NLP engine knows, okay, this user is asking about an order. So this is the order, and we try to query the order management system perhaps, and then try to get the states. And if you want to ask the delivery state, probably have to go to delivery tracking system. Likewise, all this backend processing happen. Once we know the result or the insight of the query, we will again pass it through the NLP engine and push to the client. Could be WhatsApp or Alexa or something like that. So where the coroutines come in, you can see this component called a coordinator. It is by nature, this application was fully asynchronous, because these channels are asynchronous. You don't have to wait. You can do everything pretty much asynchronously. So this asynchronous communication actually helps in a way where you can scale and you don't have to worry too much about the shared state. And also we adopted this. This was a monolith, and then we used this web framework called Vertex, and Vertex has this built-in coroutine support, which is a nice, fast, netty-based web server. And the coordinator is the component which, when you get the events from order management system, delivery tracking system, or payment gateway, it keep track of which event is this and then try to perform relevant task. So that was the idea. So I'm going to show you the code here, and you can see kind of a simplified version of event coordinator. For example, let's say we got a call from order management system because user asked for order status or something. And then when you get this order event, we look for, okay, what's the status? If it is a create one, we just perhaps go and handle the created event and wait asynchronously. And also, if it's a new order, we want to create a new delivery task, and then return the task ID and move this task ID to another stage. Likewise, there were a series of multiple steps, and there were like aggregations and waiting for different outcomes. So this coordinator was a very good example. I when I designed this and I developed this, I came to mind that okay, this is a coroutine is one of the good use case and good a way to simplify and make this code more readable. And it is actually one other thing is because of the we wanted to run these services in very lightweight, easy to VMs, and we wanted to keep things lightweight and cost effective. So that's actually helped as well because Vertex in one hand is very lightweight and it was basically good web framework, and on top of that, Kotlin Coroutines actually complement this server. So actually, that's pretty much it in terms of the example and code. So I would really like to hear any questions or anything if you want to discuss anything. I think we have some few minutes.
Awesome, that's really cool. Thanks, mate. I'm just curious around kind of how you go about testing this stuff. Into coroutines in general, backend coroutines, things like that. Does that kind of make it more complicated? Is it easy to do?
It actually, that's a good question because it actually does the testing a bit complicated. In terms of it's a naive or the simple way is just to when you run the test, you can see that in Kotlin coroutine guide they provide these test utils. Usually you have to do the testing inside the run blocking type of construct. So because if you do the run blocking, it always works because it's almost like a non-asynchronous code. But testing, if you want to test like event passing, or maybe if you are using like channels, it's a bit hard. It can introduce flakiness, and at least on my use case, you are able to do that using a run blocking type of a sequential testing approach. It wasn't that hard for that, at least that project. But I know there are could be challenges due to in testing.
Awesome. So I got one question: should coroutines be used instead of threads futures?
Right. Yeah. So yeah, I'll say that. I mean, coroutines is not like it doesn't really fix one of the major issues in threads, for example. It doesn't really prevent you from corrupted shared state, I would say. So in usual, if your language supports and if you want to do lots of asynchronous processing, and if the data is quite immutable, I would recommend going with coroutines because it's more readable and it's very easy to easy to write the code against it, and you see more confident with the coroutine code rather than traditional threads or something. But futures and promises, again, if you think the coroutines, the way it tries to return values are quite similar to futures and promises, because if you look at this code again, this asynchronous construct here, especially in this one, if you want to return something, you need to have a deferred object. So this deferred object is basically something similar to a promise. I think if you have the right support and if you have the language support, I would go with coroutines because again, this maintainability and readability. I don't think there's anything we cannot achieve from threads, promises or futures. But again, about the maintainability and readability aspects, I would go with coroutines.
Awesome. Really appreciate that, mate. Thanks a lot. That was awesome. Again, I'll put your contact details in the chat if anybody wants to kind of reach out. And thanks again. That was really cool.
Yeah, thank you. Yes, I will do.